Welcome, everyone. Today we'll be taking a look at the lesson entitled Families of Functions. The beginning part of this lesson will just consolidate some of the work you've already done with functions. And then as we get a little more into the lesson, we'll explore a very particular type of function, both graphically and algebraically, and then do a really good application to kind of wrap this lesson on up here. So let's go ahead and start right away, just working with some of the graphs, just refreshing memories on domains and range. But the idea is to go through this front side pretty quickly. And at the end of the front side, when you look back on it, the idea is that you understand each family of function produces a particular type of pattern on the coordinate plane. And you should be familiar with the type of pattern that each of these functions does produce on the coordinate plane. So let's start that out. Just what I've chosen is really the most basic of each family of functions. So, we all know linear functions are in the mold of y equals mx plus b. So again, here's just your most basic one. What is the pattern that it forms? And then what would be the domain and range as a result? So if I was to graph, obviously, a linear function, it forms a line on the coordinate plane. This would be the line specific to this particular function. And what would be the domain? Well, as I go left to right forever and ever and ever, we would say all real numbers. And as I look at the range, talking about the vertical values on the graph of these functions, we would also say all real numbers. And again, at any point, if I go through this a little too fast for you, please highlight it in your notes and then just remember to ask me about it and I can take it a little slower. But to me, this is not necessarily the crux of the lesson. To me, the crux of the lesson begins on page 2. All right, so quadratic family of functions. Here's your most basic one, just y equals x squared. So everybody, if you would, let's go ahead and draw a parabola on the coordinate plane, which we know should be the case for all those quadratics. And so it looks something like that. This would be the U-shaped curve for every quadratic function. And in terms of domain and range, we would see again that the domain is all real numbers. And in this particular case, the range, it looks like from a vertical perspective, there is a minimum down here when I have a y value of 0, and then the graph is just represented from there on up. And so we can do this in interval notation. I'm just going to use an inequality there. Y is greater than or equal to 0. So we've got our x to the first graph, our x to the second graph, then we go to our cubic, which would be our polynomials of degree 3, and to just graph the basic y equals x cubed. X cubed graphs looks something like that. Again, the most basic one looks pretty much like that right there. And domain and range for our cubics, all reals and all reals. Again, just getting used to the graphical pattern produced for each of these individual families of functions. Square root functions, another one where we'll go ahead and explore the details here. And so it makes a coordinate plane, and in actuality, it just starts at the origin and goes through that first quadrant, like you see there. So I've been doing a lot of domains of all real numbers, but that stops because if you notice, as I think about this left to right, I do have a point that is on the leftmost portion of the graph, and then it stops. So there is no graph to the left of this particular x value of 0. So it seems like I'm getting an x value of 0, and then obviously the graph is represented there and to the right of it. So we would say x is greater than or equal to 0 for the domain. And in terms of the range, I just need to get a vertical perspective on this. Same idea, I've got a low point there at the origin. So that low point has a y value of 0, and then the graph is represented up from there. So same deal, just greater than or equal to 0. And that makes sense if we're talking about a real number system, of course. Domain, well, x has to be greater than or equal to 0. In the real number system, I cannot take the square root of a negative. And that's what this indicates right here. All right, so again, just first 4, knocking them out. Let's move on to the last 4. So the next family of functions we'll take a look at graphically would be the rational functions. So rational just means fraction. And you see the most basic one right there. And this forms a nice, what's called hyperbola on the coordinate plane. So something like that. Draw my arrow. You'll do a great job on that. You'll do better on your paper, I'm sure. So it looks something like that. right there. So a nice hyperbola where we have what is called a vertical asymptote, if you remember that terminology, and we also have what's called a horizontal asymptote. In terms of the domain and range, I'm going to simplify this essentially, but x can be anything except 0. So if you notice as I go left to right here, it's coming down, it's getting closer to the y-axis, but when I hit the y-axis, I actually have to pick up my pencil and then start drawing it on the other side. So I'm jumping over an x value of 0, and so that value is excluded from the domain. And it just so happens with the range, same deal. Okay, so hyperbolas for our rational functions, moving over to absolute value functions, and should be comfortable with having seen this before. But the absolute values form a V-shaped pattern on the coordinate plane. And in terms of the domain and range, we're going to go all real numbers on the domain, of course, and the range. As you can see, I've got a minimum at the origin there, so a y value of 0, and the graph is represented above it. Now again, just want to be clear, obviously as the complexity of these functions change, your range or potentially domain could change on any of these, so just be aware of that. As I said, these are for the most basic ones out there for each family. All right, exponential growth curve. So again, potentially you've seen this before. Looks kind of like that right there. Again, just should be comfortable with the graphical pattern of exponential growth. And it turns out that the domain would be all real numbers. And the range would be greater than, but not equal to 0. We get what's called a horizontal asymptote on the x-axis. And so what's going on here, as we move to the left on this coordinate plane, the graph is continuing to go down and down and down, but it's getting infinitely close to the x-axis, but we'll never actually touch it or cross it. And lastly, the logarithmic growth function. So one more coordinate plane, if you would. And logarithmic growth, and by the way, we will see a nice relationship between a logarithmic function and an exponential function. But for right now, just want us to get used to what that graph might look like. And it looks something along those lines right here. And for the domain, everybody, because it has a vertical asymptote on that y-axis, the graph is only to the right of the y-axis, so greater than 0. But the range, if I think vertically, it's going down forever and ever and ever, and it's going up, although it's plateauing, but it is continuing to rise forever and ever and ever. So all real numbers on the range. So what I'd love for you to do is just take 30 seconds and just stare at these for the moment and just be comfortable with the type of pattern that each family produces on the coordinate plane. All I need you to get out of it, and get a little refresher on domain and range as well. All right, we are going to go on to the next piece. So what I want to do is spend some time looking graphically and algebraically at what is called a piecewise defined function, and that's what you see here on the second page. And then when we hit the third page, and yes, there is a third page, we'll do a really good application and try to put all our conceptual understanding together in one big, massive problem there. Okay, so a couple things that we're going to take a look at here. So it is called a piecewise defined function. And as it states, it is a function defined by two or more equations. And the use of the equation is based on the domain. And so here is an example of a function. Now I just want to be clear about one thing with these. It is one function. So it's y equals, or f of x equals, obviously that means the same thing. So it's one function, and it's just broken up into different parts, different expressions here, based on the domain interval. So we would use this expression for x values that are less than -2. We would use this expression for x values in between -2 and 3. And we would use this expression for x values greater than 3. So you can see expression here is telling us that it's conditional, and in the domain intervals over here. All right. So what I'd love for us to do is to just try to graph this on the coordinate plane. Now notice it says graph this function, and I know it seems silly. Why am I honing in on this idea that it's a function? Remember, if it's a function, it has to meet a couple criteria. Algebraically, the idea is each input produces one output, and we should see that here. Graphically, remember, it should pass the vertical line test. And so we want to see both those pieces come to fruition here. All right, so a couple things to know. This is broken up into 3 parts, so 3 domain intervals. So what I want you to just write here, maybe off to the side, is we're going to have 2 breaks in the graph based on 3 domain intervals. Okay, so just jot that down there for yourself. So 2 breaks. There's going to be a break at -2, because here's less than -2, and then here's greater than -2. So what I want you to do, as lightly as possible, I have a tough time doing this with my pen on the board, so you're going to do it with your pencil though, as lightly as possible, in x value of -2, I just want you to go ahead and draw a vertical line dotted kind of like this, as light as you can. So there's going to be one graph to the left of it and another graph to the right of it. So there's a break when x is -2. And there's also a break when at +3, right? Because we're seeing one expression used when x is less than 3, less than or equal to, I understand, and then one obviously to the right of 3. So what I want you to do, again, go over to an x value of 3, 1, 2, 3, and very lightly, if you would, just draw yourself a dotted line. Now we are going to erase this dotted line at the end, but for our purposes here, I think it helps us graphically. Okay, so now what we're going to do is just graph each of these expressions, but we're only going to do it in the domain interval that is specified to the right side over here. So here's what I mean by that. So we're going to graph y equals 2x plus 3. Now of course, it's just a line, right? So the y-intercept is 3, the slope is +2, so this means up 2 over 1. So what I would officially do, and don't do this on your paper just yet, please, because I'm going to do a little erasing. But I would do this. I would be like, all right, so y-intercept is +3, and up 2 over 1, up 2 over 1, et cetera, and then I would draw a line right on through, right? But the only problem is I'm only supposed to be seeing this line to the left of -2, to the left of the boundary that I drew in here. So if you want, you are more than welcome to, and I've seen students do this for sure, you are more than welcome to go ahead and draw the line in like this for the moment. But in reality, I only want a particular part of this line. I only want the line to the left of my very light vertical boundary right here. So that's what I want to do. Now I'm going to have to do it here, is I'm going to have to erase that part of it. So does everyone kind of see that piece? Now, I'm going to do one thing with it in a moment, but I'm going to hold off and continue on with this right here. So, again, this part, not the full line, only the line, only the part of the line that is to the left of that vertical boundary that I drew. Okay, now, if I said to you, go ahead and graph y equals -x, you would, of course, have a y-intercept at the origin. Slope is -1, so you'd go down 1 over 1, down 1 over 1. And you would draw, this time I'm not going to actually draw it in, I'm just going to show you with my pen here. You would draw a whole line, right? Okay, but I don't want the entire line. I only want the part of the line that is in between the two boundaries that I drew, because that's what it says. It's in between an x value of -2 and +3. So again, rather than drawing the whole line, I'm just going to draw the part of the line from there to there. Cool. And then lastly, I look at this last expression right here, just y equals 1. Well, you potentially do remember this, but when you graph y equals 1 on the coordinate plane, having a y value of 1 is just a horizontal line with a y value of 1. Okay, that's great. But do I want to draw the entire line from start to finish, left all the way to the right? No. I only want the part of the line that is to the right of positive 3, meaning to the right of that vertical boundary right there. So rather than drawing it all the way across, I just draw it from there. Okay, now what I would love for you to do is take a moment and very lightly, let's go ahead and get rid of those boundaries. Okay, there's one more thing we want to do, and then I'll highlight one last piece, and we'll move on. So, first and foremost, we do have to be careful about how functions are defined. They have to pass the vertical line test, and I see one issue with the way I have it right now. If I was to draw a vertical line right here, it does actually look like the function is defined in two different spots. And again, this is just based on the way I drew it. It looks like it's defined here and also here. And that can't happen. That would make it not pass the vertical line test. So in order to get it to pass the vertical line test, I have to use what's called an open circle and a closed circle. And it's based on the not or equals or the or equals underneath the inequality symbols right here. So here's what I mean by that. This expression is defined to the left of 2, and then all the way, left of negative 2, and then all the way up to negative 2, but not including negative 2. So we use an open circle. That's meant to be an open circle right there when x is negative 2. So the function is defined all the way up to, but not including that point. Whereas the expression is defined here for when x is negative 2. So we use a closed dot on this. And as a result, everybody, now it passes the vertical line test. Because if I draw a vertical line, yes, the function is defined here, but it is not defined there. So it only touches the function in one spot. Same thing at this particular junction right here. So if you notice, closed dot on the 3 for this particular part of the graph. So there, closed dot. But notice, not or equals here, so we would say open dots at that particular point right there. So meaning that we would use this particular horizontal line all the way up to, but not including positive 3 as we get infinitely close to it. And notice, now it passes that vertical line test perfectly. One function broken up into 3 parts. 3 algebraic expressions, 3 graphical parts on the coordinate plane, passing the vertical line test so it's a single function. All right, perfect. So we saw that graphically. Now let's go through it algebraically. Remember how functions work, everybody. One input produces one output. So it says, use the piecewise defined function from above to determine the following function values. So remember, everybody, when you see f of negative 4, that negative 4 is the input. It's the x side. Now, one thing with this is you don't put it in 3 different spots, right? I don't put it here and here and here and get 3 different answers. One thing goes in, one thing comes out. So the question is, where would I put this? Do I put it in the top expression, the middle expression, or the bottom expression? Well, it's based on the conditions set right here, right? And I look at negative 4, and I ask myself, is that negative 4, is it less than negative 2? Is it in between negative 2 and 3? Or is it greater than 3? And of course, negative 4 is less than negative 2. So if that's the case, then it goes in here. So it goes into the top expression, so I would input negative 4 in for x, so I would do 2 times negative 4 plus 3, and lo and behold, the output would be negative 5. Input negative 4, output negative 5. Now, by the way, everybody, this should absolutely correspond with what we put in graphically here. X value of negative 4, y value of negative 5. Let's see it. 1, 2, 3, 4. 1, 2, 3, 4, 5, right there. See that point? That's this. F of 0. All right, everybody, which domain interval does it satisfy? Is it less than -2? Is it in between -2 and 3? Is it greater than 3? Well, obviously it's in between -2 and 3. So it goes right in here. Opposite of 0. So you would say, okay, if the opposite of 0, well, obviously it's 0. Perfect. Where is it on the coordinate plane? It's right here. This point, one input producing one output, comes up as an X and a Y right there. All right, 1.5, where would that go? Top, middle, or bottom? 1.5 is in the middle domain interval, so it goes right in there. So I just do the opposite of 1.5, and so it equals -1.5. And of course, we would see that right here. And lastly, f of 5, which domain interval does it satisfy? Top, middle, bottom. Well, 5 is definitely greater than 3, so it's there. And no matter what x is, just the y value is 1. And you can see that here, right? 1, 2, 3, 4, 5. What's the y value? 1. Excellent. Let's move on to example 2. So now let's just reverse it. I give you the graph, you give me the single function broken up into however many parts. So one thing I would write, and I think this is helpful, there's one break in the graph. So 2 domain intervals, and I'll show you how I kind of think of this as I begin to write the function. So one break, so 2 domain intervals. So here's the idea, everybody. I'm going to just do it right off to the side. I do it as f of x equals. You can do it as y equals. I cannot, for the life of me, draw this kind of bracket. So, sadly, I just do a squiggly. You do whatever the heck you want there. Maybe you can do it better than I can. I'm not even going to attempt it. It's so pathetic. All right, so there's my squiggly, because it's broken up into different parts. I already figured out it's going to be broken up into 2 parts. As soon as I realize, oh, it's one break, 2 parts, what I do personally is I leave some room and I just do 2 ifs. Nice and easy. I like starting out easy. Makes me feel confident. And then I move into the next piece. So, what I want us to do, after I realize that there are going to be 2 domain intervals, and I need to figure out what those domain intervals are, I go to the break, and I draw my very light dotted line at the break. And it just so happens I'm drawing my dotted line. My break seems to be when x is -2. Does everyone see that here? X value of -2. And it seems like I'm getting one graph to the left of -2 and another graph to the right of -2. So right off the bat, one's to the left of -2, and I jumped the gun a little bit there. And one of them is to the right of -2. Now, if you notice, open dot, closed dot situation, in order to figure out it's defined at one of them but not the other, which is absolutely what we need. So if you notice, I have an open dot on the graph to the left of -2. So this is going to stay as is without the or equals. But I have a closed dot on the graph going to the right of -2, so my or equals would go there. It can't go under both. That wouldn't make any sense. And it goes under this one, again, because of the closed dot. So 2 ifs. My break is at -2. And so as a result, I have my 2 domain intervals right there. Now, one other thing that I would say, and then I'm going to let you kind of do this in some respects. For our purposes, I'm just going to give you parts of a line, because, I mean, we could do other graphical patterns, as we just saw on the front side of this lesson. But for right now, I hope you do see that these are just parts of a line that theoretically would extend forever and ever and ever. It just so happens that each one was broken up into one side of the -2 and the other side of the -2. So, long story short, can you just make a little note to yourself? We obviously always want mx plus b to represent a line on the coordinate plane. So make that note for yourself. Or I'm going to shortchange coordinate plane there. You don't have to. So again, all I'm going to do is just figure out what is this line right here and what is this line right here. So mx plus b. So slope, let's see, up 1 over 1, up 1 over 1, up 1 over 1. If I need to extend it, I would. Just kind of do this and just to get a sense of it, up 1 over 1, up 1 over 1 each case. So it looks like it would be a positive 1x. And by the way, remember, inclining line, we always kind of read our lines moving left to right. So inclining line, positive slopes. Now, what is the y-intercept? Well, it's funny. In reality, the y-intercept is not in existence because I cut the line off before it could hit the y-axis. But if I'm going to do mx plus b, I do have to extend, I have to extrapolate where would it hit the y-axis if I was to draw the whole thing. And it looks like it would hit a positive 3. So plus 3. And then this one, declining line, so down 1, looks like left 2, down 1, left 2, down 1, left 2. So negative 1/2 x. And this one does cross the y-axis. And so there we go. If I picked an x value, figured out which domain interval it was in, put it in the right expression, and get a y value, would that match up with the graph right here? Absolutely. Okay, so we went in both directions. I gave you the equation, you gave me the graph. I gave you the graph, you gave me the equation. Okay, now, the last one. So it's a great little application dealing with piecewise defined functions. And I'm going to try to explain this as clearly as I possibly can. In fact, I'm going to try to do it as visually as I possibly can for you. So if anything on here just it's not clicking, please put a little star by it and ask about it. And let's go for it. So a country taxes the first $40,000 of an individual's income at 12% rate, the next $50,000 of an individual's income at 23% rate, and any income above $90,000 at a 35% rate. So this is what is called a progressive tax system. And the U.S. actually incorporates such a system. So the idea is the more income you make, then the higher percentage on that income you would pay. But here's the for instance. If you make $100,000, you don't pay the high rate for all $100,000 of that income. It's broken up into parts. Note, the first $40,000 is taxed at that rate. The next 50 is taxed at that rate. And anything above is then taxed at that rate. So that's what's called a progressive tax system. Okay. Now here's what we're going to do in order to try to make this as visual as possible. Now, by the way, the U.S. tax system is infinitely more complicated than this, but the idea is very true to form. So here's what I want you to write. Each x represents $10,000 of income. Keep it nice and easy if I can there. And let's see what we can do. All right. So let's start it out. So how much tax would you pay if your income is any amount between $0 and $40,000? So what I'm going to do is kind of look at that top line there and then look at my little table right here. So if I made $10,000, based on the way the problem is worded, all of that would be taxed at 12%. If I made $20,000, all of that would be taxed at 12%. If I made $30,000, all of it would be taxed at 12%. So what I'm hoping you would see is all of the money that you make between 0 and 40,000 is taxed at 12%. Whatever that number is, whatever your income is, if you make less than or equal to $40,000, however much that may be, all of it is taxed at 12%. And so 0.12 is the decimal representation of 12%, times your income. So just put a 0.12x. Perfect. Now we go to part B. And in actuality, what I want you to do is just kind of highlight that piece. And then, as a matter of fact, let's kind of do these guys right there. Highlight that as well. Because these next three go together. So, letter B. If you earn more than $40,000, do you still pay 12% on the first $40,000? And this is a huge question. And I would say, without a doubt, the answer is yes. And if you take a look at the problem itself. Doesn't it even say that? A country taxes the first $40,000 at 12%. So make a little note for yourself there. The first sentence says it. Exactly that. So, let's go ahead and, now that we're into the second level of our function, this means we've now made $40,000 here. Now the money above $40,000 is going to be taxed at 23%. Okay, so I want to make sure that letter B resonates with you, and now we're going to go into letter C. So if we earn $50,000, so this is where this table I think helps. So here's $40,000 of it. There's the next part of it. Now, hopefully everybody would agree, that's $50,000 total. Based on the problem, it says the first $40,000 is taxed at the 12%, and only $10,000 of it would be taxed at the next level. So it says, if you earn $50,000, how much of that income is taxed at the 23%? Only 10 grand. If we make $60,000, okay, let's put another 10 in there. So now $60,000. How much is taxed at the 23% level? You can see it right there, everybody. 20 grand. Okay. If we earn $70,000, let's keep it going. There's $70,000 bucks. How much of it's taxed at the 23% level? Well, if you notice, it looks like just $30,000. So if I gave you any number that's between 40 and 90, how can I figure out how much is taxed at that particular level? And what I'm hoping you would see is, if I knew it's $50,000, if I subtract the $40,000, which by the way was already taxed, if I subtract that $40,000, that gives me this. If that's my income and I subtract $40,000, that's how much is taxed here. If that's my income and I subtract $40,000, that's how much is taxed at the 23%. So what I would say is, write an expression for the tax paid on income between 40 and 90. Well, guys, 23%. Not all of it. Only the money above 40,000. So I subtract away the 40,000 because we already were taxed on the 40,000 at the 12%. That's not kicking in for 23%. All right, I hope that works for you. Now the last big piece. And I just put the table here again. You'll just go ahead and use the one from above. But it looks like we are here at this stage. We are earning more than 90,000. So everybody, put 90,000 into the mix. Okay, and what I want you to do is loop up those guys right there. All right, so we've got 90,000 in our table. Now we'll start talking about money above 90,000. So, letter E. If you earn more than 90 grand, do you still pay 12% on the first 40,000 and 23% on the next 50? Yes, and yes, of course. And by the way, doesn't the problem exactly state that? Look at that. Country taxes the first 40,000, 12%, the next 50,000 at 23%. That's exactly what it says. And there it is in my table. First 40 at 12%. Next 50 at 23%. How much income is that total? That's $90,000 total. So this rate only kicks in for the money above $90,000. And again, I would just say right here, first sentence, statement. Okay, let's go get them. So letter F. If you earn 100 grand, so I've got 90 in my table. Here's one more. There's 100. How much of that is taxed at the 35%? Well, it looks like only 10 grand, right? Okay, if I make 130,000, so let's go a few more here. There's 130,000. How much of it's taxed at 35%? Just 40,000. Are you starting to see what's happening here? To figure out how much is taxed at each? I've already accounted for 90 grand. So all I have to do is take the total income and subtract 90 grand. And I'm not going to put all my X's in for this one, but you can start to get the idea. So write an expression for the tax paid on income above 90,000. So that's the 35%, X minus 90,000. Because we already have been taxed at those lower rates for the first 90,000. So this rate just kicks in for anything above 90,000. So I subtract away 90,000. That tells me how much is taxed at that rate. Now, here it is. All the marbles right here. The big asterisk by. Let's see if you are getting it. And what I want you to do, I'm just going to put a little dot, dot, dot here, because obviously that just continues. Any money above 90 grand then is taxed at that rate. So what we are going to do, everybody, is write one function. And that's the idea. It's one function broken up into multiple parts. In this case, not to give it away, it's broken up into 3 parts. So we're going to give one function, one set of rules, where you can calculate the tax based on any particular income. Tax depends on income. So everybody, T of X equals big squiggly, geez, that's horrendous. Now I'm going to leave a lot of room right here. There are 3 conditions. So as a result, let's start out easy. 3 ifs. Okay. Now there's one way to calculate the tax if we make anywhere from 0 to $40,000. There's another way to calculate the tax if I make anywhere from 40,000, more than 40,000, so notice no or equals on that, all the way up to and including 90,000. And there is a third way to calculate the tax if I make more than 90,000. Here's what I would love to see. Can you pause the lesson, see if you can come up with the 3 algebraic expressions based on what you answered A through G? Okay? I'm going to go for it. Easy level, medium level, hard level. Let's start with the easy level first. Do you remember what you answered for part A? That's it. If I make less than 40 grand, all of it's taxed at 12%. Now, for the middle level, it gets a little harder. What I want you to do is look at your answer for part B, and then look at your answer for part D. So highlight that, B and D. So if I make more than 40 grand, wasn't the first 40 grand taxed at 12%? There it is, guys. There it is in my table. All of that is taxed at 12%. So it's 0.12 times 40,000. And then the 23% kicks in for just the amount above 40,000. That's a big piece right there. I want you to see that. So again, if you look at your answers of B and D, first 40,000 is taxed at 12%. Above 40,000 is taxed at 23%. Those are the two that added together would give you the tax. And lastly, the hard one. So in order to write this, look at your answers specifically from E and then G. So if we make more than 90 grand, in fact my table is already pretty much set up for it. Look at the way it's lined up, everybody. Do you see that the first 40,000 up is taxed at 12%? There it is definitively in my table. First 40 grand, taxed at 12%. So there, all done. The next 50 grand, there it is, everybody. There's 50 grand. Isn't that taxed at 23%? So again, definitively, if I'm making more than 90,000, the first 90,000 is broken up into these two rates. First 40 here, next 50 there. Then the 35% kicks in just for the amount above 90, because I've already been taxed on 90, right? 40 and 50 make 90. So now the 35 gets kicked in for just the amount above 90,000. And if I gave you any amount of income, you would look at the domain interval and you'd say, it fits this particular domain interval, whatever it would be, and you would know exactly which expression to put it in. Okay. You don't, for this, and I would actually say, don't simplify these. It's great to see your thought process with this when it's unsimplified. So I'm going to leave it just like that, rather than trying to combine like terms and stuff. All right, guys, thanks so much. Really appreciate it. Ask for help if you need it.